Hello everyone. Today we will discuss about the AC applied to resistor, inductor and capacitor. We will derive phase relationship between the current and the voltage in all the three cases. We will draw phasors and the graph for variation with time. So let's consider a case where the AC is applied to a resistor. Second case is AC is applied to an inductor, and third case is AC is applied to a capacitor. So when it is applied to a resistor, we can draw the diagram like this. For AC applied to inductor, we can draw the diagram like this, and for capacitor, in all the cases AC is the input and the time varying EMF is shown by E naught sin omega t. So let's write down first that this is the input AC. Now we have to find the phase relation between the current and the voltage. So what will we do? We will use that the total EMF is equal to total voltage. You can write down like this. This E is equal to IR, and this can be written as E naught sin omega t is equal to IR. For finding the expression of current, you can write I is equal to E naught upon R sin omega t. If we compare it with the equation, or you can say the Ohm's law, V is equal to IR, I is equal to V upon R. So from here, let E naught upon R, we mark it as I naught, that is the peak value of current or the maximum value of current. Then we can write down I is equal to I naught sin omega t. Now let's compare equation 1 and 2 for the phase relation between current and voltage in this case. The phase difference, which is noted by phi here, between voltage and current is how much? Let's check out. Here we have sin omega t, here we have sin omega t. The angular part of the trigonometric function is called as phase, because phase gives the position and direction at a particular instant. So you can say that this is the phase part, and here in this case this is the phase part. So look at this, this is also sin omega t, this is also sin omega t. So what's the phase difference between current and voltage? Both are in the same phase, so phase difference is 0. That means no phase difference, or you can say current and voltage are in same phase, right? Then if these are in same phase, so if we want to draw the graph will show that when the current is maximum, the voltage will also be maximum, right? And in the phasor diagram also, both the phasors will be in the same direction. I want to draw a comparative diagram for phasors and graph for all the three cases. So I'll draw both the things on the next slide, because here for inductor and capacitor I need more space to derive this part. So phasor and the graph, I'll show it on the next slide. Now let's take the inductor. We know that the same AC voltage is applied over here. Let's mark it 1. Now we know that this is a time varying quantity. This AC is time varying quantity. Now we know that this is time varying EMF. So as this EMF changes, or you can say that the current changes here, and that's why an induced EMF and induced current is developed here. So this is the supply EMF, and here some back EMF, or you can say the induced EMF, is also developed. So if we apply this concept that total EMF is equal to total voltage, this is a trick, in fact, not a rule, not to be written. So this is just to remember this. Now total EMF means the supply EMF plus the induced EMF which is developed here, and this is equal to total voltage. Total voltage means current into resistance. And for a pure inductor, we consider that the resistance of the coil winding is negligible, or it is 0. So that's why this right side will be 0, and this is E naught sine omega t, and this is minus L di by dt. If you remember that induced EMF is equal to minus d phi by dt, and this is Li, phi is Li for an inductor, so you can write this is just a recalling of the concept. If we solve it, we'll get E naught sine omega t is equal to L di by dt, because we are shifting it towards the right side. Now we have to find the phase difference between the current and the voltage. So we need to find the expression of current. How will we find that? We know that we can keep it here di on one side. Rest of the things can be shifted on the other side. So integrating it, we will get the current expression. So this can be written as, I am switching the sides, so di is integrated as I, and E naught upon L can be kept outside the integral sign, and this will be integrated, and after integrating there will be a constant of integration. Constant of integration. Let's solve it. I is equal to E naught upon L. Sin omega t has an integration minus cos omega t upon omega by chain rule, because this is not simply t. So omega t will also be integrated once more. So this will be divided here. So this is equal to omega plus constant of integration c. Now this I is a time dependent quantity which varies about 0 value. This is also a time dependent quantity which varies about 0 value, and this is a constant of integration which must have dimensions of current. So this constant must have a value 0, that's why we are writing this 0. So we can write the reason here. I is equal to time dependent quantity which varies about 0. Simply same way, cos omega t is also time dependent quantity which also varies about 0, and c is a constant with dimensions of current. So as per this equation, this must also have a value 0 in order to have the equation E naught upon omega L. This is minus cos omega t. I will just mention it. Therefore C must be 0, right? And we have to compare the phase of voltage and the current. So for comparison, this trigonometric value must have the same form, and the sign of the trigonometric value must also have the same form. So here it is plus, here it is sin omega t. So in order to convert it into plus and sin omega t, what can we do? We can write down by applying trigonometrical operations. This can be written sin omega t minus pi by 2, and this value can be written I naught where E naught by omega L is equal to maximum or peak value. Right? So if you look at this expression, equation 1 and equation 2, then we can infer from here that the voltage leads the current by pi by 2, or you can say current is behind the voltage by pi by 2, right? So here we don't have space for comparative statement. I am simply writing in short over here that voltage leads current by pi by 2 in an inductor, right? Similarly, for capacitor, we can use a similar concept. We know that this is the voltage applied, and we know again total EMF is equal to so you can write down E is equal to V, and this can be written E naught sin omega t and this can be written as, you know the relation, Q is equal to CV. So therefore V can be written Q upon C. Now this is Q upon C. Now we have to find the current value. Current can be written as dQ by dt. So we can write down Q is equal to C epsilon naught sine omega t. So therefore dQ by dt is equal to C E naught, and sine omega t is omega cos omega t. One step I have missed here. C d by dt of sine, let me write it again. Left side can be written as current, and this is constant, this is capacitance is constant, E naught maximum value is constant, so this can be taken outside the differential sign. Now on differentiating it, sine omega t is omega cos omega t, because sine omega t differentiation is cos omega t. Now this is not simply t, so this omega will be multiplied here. Now this can be written in this form. Where I naught is equal to C E naught omega. Now we have to compare this equation and this equation. Now these are not in same trigonometric form. This needs to be in same trigonometric form for comparison. So therefore this can be written as I naught sine omega t plus pi by 2. Sine 90 plus theta is cos theta. Therefore this is written like this. So now we can compare this equation 1 and 3. We get, look at this, E naught I naught sine sine, so phase mein this is omega t, this is omega t plus pi by 2. So you can say that current leads the voltage by pi by 2 in a capacitor. Here you can mention that you have comparing 1 and 2, right? So here in these three cases we have derived the phase relation between the current and the voltage in all the three cases. Now on the next slide, I'll first write the other form of this statement, leads and lags, and then we will draw the phasors and the graph for all the three cases. So let's take the another slide. So what results have we derived? We have derived that current and voltage are in same phase in a resistor. So therefore if we represent the phase difference by phi, then this is 0 in case of a resistor. In this case, voltage leads the current by pi by 2 in an inductor. Now how to remember this? You remember this by trick VLL. This is trick. Voltage leads the current in an inductor. Now in this case, the phase difference is pi by 2, right? And in this case, the current so here this phase difference is pi by 2. In this statement, the language may be written in different form also. You must remember that also. Here, current lags behind the voltage by pi by 2. In this case, voltage lags behind right. So remember any one thing, you will be able to frame the other things. So if you remember VLL, you will be able to frame this statement for capacitor because this is reverse of this, and lags can be framed if you know, a lag statement can be framed if you know this statement. Now let's come to the graph. Graph between current oblique voltage with omega t. This is not upon, this is or. We know that current and voltage are in same phase in resistor. So we know that the voltage is sinusoidal, E naught sin omega t. So in all the cases, this is the voltage, must be symmetrical. I'm drawing a free hand, so I or in this case the current and voltage are in same phase. So this is also sinusoidal. Now in this case, the voltage leads the current by pi by 2. So voltage is obviously this because this is sin omega t in this case. So sinusoidal graph starts from 0. So we can say in all the three cases, this value is the maximum value of voltage or the peak value of voltage. In this case also, this is the peak value of voltage, right? And we are talking about the current in this case. So what is the expression for current in this case? You know that E is E naught sin omega t and current is I naught sin omega t minus pi by 2, right? So that means you can say that this is minus cos omega t. So if you put t is equal to 0 here, this will be sin minus pi by 2. Sin minus pi by 2 is minus 1. So this is I is equal to I naught sin omega into 0 minus pi by 2. So this gives me minus I naught at time t is equal to 0. So at time t is equal to 0, the current will be minus I naught here. So if we draw the expression of current, it will be like this. So this is minus I naught and this is right, and this is the complete cycle. We can mention 2 pi. This we are showing in terms of angle. Omega t is angle, no? This is pi. This is pi by 2 and this is 3 pi by 2, right? Similarly, this is omega t. So this is 2 pi, this is pi by 2 and this is 3 pi by 2. And in terms of time period, if I write, this will be, if we write in terms of time period, then this will be t, this will be t by 2, this will be 1 by 4th time period and this will be 3t by 4 time period, right? So I am not mentioning everywhere, I have just mentioned in the first case here. Now in case of capacitor, the current leads the voltage by pi by 2. So if you remember the expression, this is E naught sin omega t and current is I naught sin omega t plus pi by 2. So if you put t is equal to 0, so sin 90 is 1, so I will be equal to I naught. So that's why at this point the current will have maximum value in positive direction. So right, so this will be your current graph. Here it will be maximum when this is 0. Pi by 2 phase difference means this only. This is also sinusoidal, right? So this is plus I naught value and again this is 2 pi, this is pi, this is pi by 2 and this is 3 pi by 2 if we are writing in terms of omega t or angle. So this was about the graph. Now we have to draw the phasor. So for phasor also I would like to take a new screen, okay. Now for phasor, we know that phasor is a rotating vector. We are representing this voltage and current, which are scalar quantities, in the form of phasor here, because these are also sinusoidally varying in case of AC. And sinusoidally varying quantity can be represented by phasor diagram, which are rotating vectors which are rotating with the frequency omega, and their results, the time sinusoidally varying scalar quantities on analysis give the same results as that given by the phasors. So that's why for simplicity we use the phasor, that is the rotating vector, for solving the complicated phase difference cases for voltage and current which are sinusoidally varying in AC, right? So if we are drawing a phasor for resistor, what will be the difference? Let's see. Here voltage and current are in same phase. So if this is the voltage phasor, so this value gives the peak value, and this is having frequency omega. And if we are drawing a current phasor, because current is also in the same phase, so this will give you the current phasor, and this magnitude of the length gives the magnitude of the peak current, and peak voltage is given by this phasor. Now if I want to know the time varying value of voltage at any time t, we can draw the projection of these phasors. So for projection from this point and this point, we will drop a perpendicular, and this gives you the projection of this E naught, and this by trigonometry is, this is not necessary to be drawn, this is for explanation I am drawing here. So this will be E naught sine omega t, which is the value of EMF at any time t. So if I take the projection of the current phasor, then this will be the projection of the current phasor, and this will be I naught sine omega t, and this gives you the current value at any time t. So this is the phasor for resistor. Now in case of inductor, the voltage is suppose represented by this, because E naught sine omega t gives you the voltage at any point. So its projection will be given by this perpendicular and this perpendicular. So this will be E naught sine omega t, and this is giving the value of voltage at time t. We know that voltage leads the current by pi by 2. So leads the current means we consider it anti-clockwise. So if we want to draw the current, so this will be at 90 degree here. This is I naught. The peak value of the current is given by this phasor, and if I want to know the time varying value, this will be and this is minus pi by 2, so this will give you minus I naught, right? So this is the phasor for inductor. Now for capacitor, if we are drawing this as the peak value of the voltage, then obviously the foot of the perpendicular of the ends of this phasor will give you the value of EMF at any time, and in this case the current leads the voltage by pi by 2. So if I want to draw the current phasor, it will be 90 degree here. This is I naught, and this angle is omega t, because in this case this is E naught sin omega t, and this is omega t plus pi by 2, as clear from the figure also. So this value of angle is omega t plus pi by 2, and this projection of this gives you I naught sin omega t plus pi by 2. So this was all about the phasor, the graph, and the phase difference between the voltage and current for a resistor, capacitor and inductor. That's all for now. Have a nice day.